All right, so let's go ahead and take a look at some of the information necessary to complete a selection of questions from the test 2 material. So for this first one, we want to look at a pair of masses that are set apart at a certain distance. So we're going to find something called the gravitational force between these. So gravitational force, we talk about between large objects typically, it gets a capital G because it uses a constant that is a capital G. Then typically you'll have either M1 and M2 or sometimes a little m and a big M for different masses, but because this is a pair of identical masses, we can just put big M and big M. Or, you could call them 1 and 2 if you wanted. It's the same either way. Okay, and then what's the next thing that's important is the separation distance squared. Okay, so M equals M, right? They're the same, that's why I made them look the same. We want to keep in mind that if it's a billion kilograms, then that means that that's times 10 to the 9 kilograms. So I'm going to want to use it that way so that I can put scientific notation in the calculator. Then I also want to think about this being kilometers. Because I'm already using scientific notation, we want to say that that's 10 to the 3 meters, which is the same as 1,000 meters, because 1,000 has 3 zeros in it for the exponent 3. Okay, and so if we run through and we calculate here, G is a universal gravitational constant, roughly 6.67 times 10 to the negative 11. Excuse me, negative 11. Now the units are complicated, but they're made basically to cancel everything else. So newtons times meters squared over kilograms squared. Okay, it makes sense at least on the one part because we want newtons as an answer, but we'll see where the rest of that's going to go in just a minute. So pair of masses, 1 billion each. So 1 times 10 to the 9. If they'd been 3 billion, it'd be 3 times 10 to the 9. If it was 1.4 billion, it'd be 1.4 times 10 to the 9, and so on. And then there's 2 of these identical. So I'm just going to rate that again. And then all of that goes over the separation distance squared. So 8.2 kilometers, I'm going to write as 8.2 times 10 to the 3 meters. And now what this does allows us to see the units. Kilograms cancel with kilograms and kilograms here. Then meters squared cancel with meters and technically more meters in the same place. Okay, and then depending on your calculator and your comfort level with typing in scientific notation, there's a few different approaches from here. Technically, you can type this in the calculator all at once if you're really careful. You may need to use additional parentheses in some calculators. What I would recommend, though, is work out the numerator, then work out the denominator, and then finish from there. Nice thing about the numerator, though, because these were just both ones in front of the scientific notation, we're going to get 6.67 back. Then what happens is the way that these multiply, add 9 and then add 9 again, then this is going to become times 10 to the 7. Otherwise, just manually multiply those calculator, see what it says. Then on the bottom, don't forget that this needs to be squared because of the formula. So in the end, we get 6.724 also times 10 to the 7. Now, the only units left over from earlier were newtons, so that's for sure what we're going to get here. Then technically, if you want to, times 10 to the 7 times 10 to the 7 match, and they could be canceled. And so really what we're doing is just dividing these two numbers, which are pretty close to each other. In the end, we get something like 0.991969, and I'm sure it keeps going. And then if we look at the closest answer choice, well, that's clearly very close to 1. Okay, then we want to think about this formula. If you've got the lecture and you've seen the factor sort of questions, as the students seem to call them, then this is related to that. So if we look at just the same formula, and we're not going to plug all the numbers into it this time. And we see what's here, okay? The things that are on the top of the fraction, the gravitational constant is not going to change between different questions. So what we're really focusing on are these masses. And the masses are going to change in such a way that they are directly proportional. So that means that if I double one of the masses, then I'm going to double the answer. If I double both of the masses, then times 2 is going to mean 4 times the answer. Or if I go the other way, say I do 1/3 of the mass, then I'll get 1/3 of the answer. Now the r on the bottom, because it's on the bottom of the fraction, is inversely related. Now we have to be careful because it's actually a little bit more specific than that. Technically it's inverse square because of the exponent, but we just understand that things on the bottom are typically inversely related. If r gets bigger, then the answer gets smaller. And if r gets smaller, then the answer gets bigger. So if we look, the fact that this is on the bottom of the fraction meant that it was never going to give back the same answer. And because it got smaller and we plugged into the bottom, it's going to have to be some bigger answer. So it's not going to be that one. Okay, well, let's see if we can estimate what it would be. So keep in mind, if we're only changing just the separation distance, if we're just changing r, then g is the same all the time. It's not really going to change. These masses, the old mass compared to new mass, would have the same a ratio of 1 because they'd be the same value. New mass to old mass here, ratio of 1 because it's the same value. And then ratio of the new radius compared to the old radius. Technically, we'd have 0.25 to r over r, and it would cancel. And so what we're really looking at is just that factor decimal plugged into the bottom. What you can't forget is that it's squared. So this is what it means when we talk about the inverse square relationship. If we put something in here, how would it change the answer between different versions of this question? And so you're looking at 1 over whatever the factor is, and then squared. And for this example, ends up being just a little bit under 16. There we go. Okay. Now, this one can be approached a couple of different ways. If we think about it, right, look, we can check these answer choices and they all have exactly the same number. That means that we're really just looking at the units. So if we think about gravity, right, so we've used gravity in all kinds of different questions in the past. Gravity was always equal to some number. So people usually remember that for Earth, this number is 9.8, but some number. And then the part that a lot of times students forget is that the units on the end are meters per second squared. Only one of these that could even possibly be the answer is this one. This is reverse. This doesn't have the squared. This doesn't have seconds at all. So there's really only one possible answer. Now, normally I'd want to work this out anyway, but because I know the next question is related and uses the same numbers again, I'm going to save that work for the next one. But like I said, for this one, even just the units is enough for us to see an answer. Okay, so let's see one where we actually have to follow through and do the work. So we want to be careful here because all of these answers look more or less the same, just with the decimal shifted around. So, we need to see what it looks like it's going to be. All right, so our formula should be on the formula sheet, and if not, it's on the lab activity. But we have 2 times the change in length. So here it's the change in y because we're going to allow something to drop, divided by time squared. Okay, the time is fine because that's in seconds, and that's typically how we measure time. But that change in height or change in y position here is not fine. We want typically meters. So to the side, 86.42 centimeters. So 100 centimeters make a meter, just like how there's 100 cents and a dollar. You can also sort of eyeball this and see that this is definitely less than a meter. So when we convert it, it should be an answer that's less than 1. If you go the wrong way and you get like 8,000, then that should be a really big clue that it's wrong. Okay, so centimeters and centimeters will cancel from this work, and that was intended. Then we get meters as an answer. That's what we're trying to get to. So I'm going to go back and destroy the evidence, and I'm going to plug in the old number accidentally. And this is going to turn into 0.8642 meters. Okay, and then from here I actually have everything I need to plug in. So gravity, from this experimental group, we've got 2, which is just part of the formula. The change in y position, which is the distance in meters that this was dropped. And then over the time squared, which is given to us. So we have the time Easy enough to just square it. If you look at the units, we've got meters here and seconds that get squared. So that's our meters per second squared that we would have seen on the last question. If we go ahead and double the top, we will get 1.7284. And then if we square the bottom, we get 0.1444. Then dividing these gives us something like 11.9695 meters per second squared. Okay, so that's just the raw value for what the group would calculate if they ran a lab and got answers similar to this. Now to do our percent error, we want to compare the true answer, so on Earth we should have 9.8 meters per second squared, minus our trial answer, and the order here is not actually super important because we've got absolute value bars, right? So if we subtracted the wrong way, we got a positive or negative answer, it wouldn't matter, we'd have the same value. So I'm going to go in and stress these absolute value bars. So the true answer minus the answer we're checking just to see how far it's off. And then the answer you trust, the one that's supposed to be correct, gets used twice. So it shows up again for the bottom, and that's intentional. Okay, so what the top does is it finds our absolute difference, just how much is it off. Then dividing here on the bottom is going to turn this into a decimal, and you have to be careful because we want percent error. So the final step is going to be times 100, slap a percent sign on it. Alternatively, you may have learned in school to move the decimal place 2 times at the end. That's fine, but it's an alternative. Definitely don't do both. Don't move the decimal place twice and multiply because then you're doubling up the step. Okay, so finding the difference, we subtract these, technically get a negative answer, but it doesn't matter because of absolute value bars. This is off by 2.1695. And then dividing by 9.8 for what proper gravity should be. That's going to cancel out these units. Then we can't forget that there's a times 100% on the end. So we're going to end up with a 0.22137755, blah, 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 times 100%, which I can just barely fit in at the bottom, makes 22.14%. There we go. Okay, so we want to determine the amount of potential energy of a pendulum at its lowest possible point. So potential energy for a pendulum, we're going to assume that it's not like a spring or anything else fancy, that it's just a swinging pendulum, a ball on a string or something on the end of a thin rod, whatever. Then the potential energy that we're looking at here is gravitational potential energy. So potential energy, and sometimes it'll be labeled with a G or even grav to say what kind. So this is going to be the mass of the object multiplied by gravity, assuming we're on Earth because it doesn't say otherwise, and then multiplied by the height or its position. Sometimes it's listed as delta H. How high is it above the lowest point? Well, what's special about this one, though, is it specifically says that it's at the lowest point. So even if we go in and we show the work, we want kilograms, so we have to divide this by 1,000. Right? Kilo over K means 1,000. And obviously that's a lot less than a kilogram, so it's going to turn into some decimal number as an answer. So we're going to have 0.068 kilograms. Then Earth gravity, 9.8 meters per second squared. And then here, this part means the rest of it doesn't really matter because our lowest possible point means we're at 0 meters above our lowest possible point. Well, these units all multiply to give joules, but it doesn't really matter if there's a 0 in the mix and we're multiplying all of those. So we end up with 0 joules. We have to actually have some height, some ability to fall and gain speed in order for there to be real potential. If it's just hanging there at its lowest point, then nothing's happening. Okay, so let's see another question where something a little bit more important is going on. So we're talking about potential energy for a pendulum. Again, we're going to assume that this is gravitational. It's not a pendulum that's also a spring or something horrible like that. So we need mass times gravity times its height above the lowest point, or change in height or position. Several different labels can work here. Similar to before, we don't like the grams, so we need to remember there's 1,000 grams in a kilogram. And we've talked about this before, but there's 100 centimeters in a meter. And so that will allow us to convert these numbers and to plug in. Okay, so the mass, 0.068 kilograms. Gravity, because we're assuming this is happening on Earth, is 9.8 meters per second squared. And the change in height, think about this. If it was 5 cents back in change, it would be like a nickel. Think about what a nickel looks like when you get it back in on the receipt. We have 0.05 meters. Okay, now if we combine all of this stuff, kilograms times meters squared per second squared makes joules, or you can combine this to a Newton first, and newtons times meters is also joules. But either way around, this becomes, excuse me, becomes joules. Then if we multiply these things together, we get something like 0.03332 joules. Looks like this top one. Okay, so now we want to talk about torque. We've got a few questions in a row where we're setting up and we're solving some torque. Now, if you have only one pivot point, then you can technically use a torque-like measurement, so not proper torque. So that's why on these questions, occasionally I'll put little air quotes, or I guess technically literal quotes on these, because we're not finding proper torque. Proper torque could be newtons times meters, but we're not going all the way there. So I'll show you why in this first example, but then I'm going to leave it out in the future examples. So if we were to do real torque, we would need 5 kilograms times gravity. Now this one's based off of one of the simulations. So gravity in that is 10 normally, but I'm going to use 9.8 because we're a little bit more accustomed to that. Okay, so this makes the weight or the force being pushed on the setup. And then the distance away is the last piece of information. We'd have 8 meters. Okay, and then on the other side, so we could say that these were like bricks being put on a seesaw or something. Then we'd have 20 kilograms. Assuming that this is on Earth, we'd have Earth gravity. And then we'd have our position, which is, we'll just say X. We could put R or something, but we don't know what this is. And here's the part why I was saying that with a single pivot point, gravity is not super important, because this has gravity and so does that, and it cancels. And even then, the mass or weight units cancel anyway because they're present on both sides. The only units we have left over are meters, which makes sense because all of our choices have meters. Okay, and so if we work with what's left over, we have 5 times 8, which is 40, and 20 times x, which we don't know. But then very quickly, we can solve and we can find x. And so notice that the heavier mass here has to be quite a bit closer to the center of the setup, like the seesaw. What we want to do is for the larger object, we want to minimize torque. Well, we can't change the size of the object without causing like physical damage to it. So we can just scoot it up. We can change the radius. Okay, so we want to see another one here, which is very similar, but this one has a different mass. So notice we've got 5 kilograms again, same position on this one, but now we have a new position for the, or another mass for the other set of brakes. Okay, so looking to set this up, we have our counterclockwise torque equal to our clockwise torque, again in quotes, because we're going to leave gravity out of this to simplify things a little bit. After writing quotes and talking about it, I probably haven't saved any time, but oh well. All right, so we have 5 kilograms multiplied by 8 meters for the position. Sorry, my pen's acting up. Let me fix my handwriting here. And then on the other side, we've got 10 kilograms and then a position that we don't know. So we'll just throw a big X there. And here's the thing. So even if we converted the masses anyway, the units and the additional conversions would have canceled each other. So we don't need that part. Like I said, if there's only one pivot point, then that works out. We have meters left over as the only units, but that's present in all of our answer choices. So that seems reasonable. Then now we want to work this through. 5 times 8 gives us 40. And 10 times x, we don't really know what to do with that yet, but that is very quickly going to give us an answer. So we don't know x right now, but you've probably already figured it out. There we go. See, if I talk long enough, we just get to the answer. Okay, now that was a relatively simple one. In the next one, we're going to have several different sets of bricks. So I just want to show what this can sort of build up to. So we could put bricks in all kinds of different positions, different masses, different sides of our seesaw or the thing that we're trying to balance, and it'll still work itself out. We're still technically not using proper torque, so we're using a torque-like measurement, but that'll help us still to solve. Okay, so we want to just sort of read through and carefully see what's sitting where. To the left and to the left, these things are going to be working together. So we're going to have 10 kilograms multiplied by 5 meters and plus sign 15 kilograms times 3 meters. And that will make some combined torque-like measurement that's trying to turn. Then we're going to have some other torque in the other direction. So notice now to the right, okay, so we've got 5 kilograms on this part, multiplied by 7 meters, and 20 kilograms that we don't know where it needs to go. If we look through our units, then everything has kilograms, so that can be canceled from everywhere. Again, that's going to happen every single time you have just one pivot point. Then for all of our remaining things, everything's in meters. And then technically this thing's a mystery, so I think it makes sense then why these are in meters. Okay, then we want to break this down and simplify where we can. So start with multiplication groupings. Here we'd have 50, and here we'd have 45, and here we'd have 35, and here we'd have 20 times x. Now be very careful here because there's a very common mistake that students make. You can add the 50 and the 45 together here because they're both plain numbers. You cannot add the 35 and the 20 together because this one has a variable. They have to stay away from each other. They're not the same kind of thing. You're breaking the laws of algebra if you try to mix them together. What's going to happen is we need to take our plain numbers and mix them with our other plain numbers. So we subtract to bring these around, and we get 60 is equal to 20 times x. So like most algebra, our general goal is to separate the numbers and letters, and we're almost there. The only thing I need to do now to get x by itself is get rid of that 20. Because it was multiplied, then we're going to divide, and then it tells us that x is 3 meters because, well, that we decided earlier it was meters, and that's what all the choices say. Okay, then a couple of questions in a row here that are just concepts, very quick and easy, and if you read them carefully, should not be difficult to answer. But let's say that I have some clockwise torque acting on an object, and it's greater than a counterclockwise torque acting on the object. So if I have a big clockwise torque and a little counterclockwise torque, then clockwise torque is going to win. For the next one, if I have some clockwise torque and it's less than the counterclockwise torque, so it means my counterclockwise torque, some really big torque trying to go the other way, then think about this to decide who's going to win. And I think it's obvious then to be counterclockwise. And then last one in the little group, if they are equal to each other. So if you have some torque trying to go this way and an equal torque trying to go back the other way, basically it's turning just as hard this way as it is that away, then they're going to balance. So if you have equal and opposite torques, then they cancel each other and it's not going to move unless it's just going to fall straight up or down. It's not going to twist in that case. Okay, then on that topic of how things twist and move, the moment of inertia is basically like resistance to turning. Different shapes and different arrangements of mass can be easier or more difficult to spin. And that's what this is looking at. Moment of inertia is the letter I, so at least the letter makes sense for inertia. And it's going to have some number in front that can change depending on the arrangement or the shape. But all of these have times meters, or sorry, times mass times radius squared. So I was thinking, in this SI part, we do need meters, so we have to adjust that in a minute. Kilograms are okay, but we don't like the way this one looks. Okay, but it's the shape that indicates what's going to be in front. Because this is a hoop or a ring or basically a hollow circle, then what we have in front is a 1, which is not really going to do anything. I suppose we can keep the color, it's still scratch work. I also want to make sure that I fix my units right quick. So before I forget, 100 centimeters, make 1 meter, and so it's going to be 0.48 meters. Perfect. All right, so let's move into this formula. The 1's not going to really contribute here, so we don't need it, so I'm going to drop it from here. The mass is 1.28 kilograms, and then the radius 0.48 meters, and then don't forget that that's going to get squared. Okay, so then the units don't really make anything nicer. In fact, here they're kind of ugly, but they make a little bit more sense if we start moving into linear or angular momentum and a couple of other things. But we get kilograms times meter squared. Okay, then don't forget we've got 1.28 times 0.48 times 0.48 again. That exponent's a clue that you're going to need to do that twice. Or depending on your calculator, you may square this first and then multiply by 1.28. If you do that correctly, though, you should get 0.294912. Looks like this first one. Okay, now the related question, I wanted to show some different options here. We are again looking for moment of inertia, so that's going to be I. Remember, that's going to be something times mass times radius squared. Mass is already good to go, so we just need to sort of flesh out our other details, and then we can get this to go to work. We don't like our radius, so 100 centimeters make a meter, and 0.48 meters. Now, this is a different shape. This is a disc. Could also work for a cylinder, but basically keep in mind that it's a filled-in circle this time. That change in the distribution of mass is actually going to change how this rolls. So we get a 1/2 in front. There's 1/2 of the inertia for how this turns. Okay, so technically with that, you might already be able to guess the answer, because if you paid attention to what the last one was, and these were the same numbers, we're just essentially dividing that by 2. But let's go ahead and set this one up. 1/2, if you want to, is the same as 0.5. Then the mass, 1.28 kilograms. The radius, 0.48 meters, now that it's been converted and squared. Okay, so remember the units are kind of ugly. They basically just get collected, brought together in one place. And then if we run the rest of that through a calculator, 0.147456, and then that's enough, right? Because we can see that's going to turn into 1475 from these choices. Okay. Then one more question, sort of as a follow-up to an earlier one. So yeah, maybe I should have moved this one. But because it's dealing with pulleys, I thought it was reasonable to go here. So we're gonna have a pulley, and we're gonna have rope that runs over it, and we're gonna have a 5 kilogram mass here, but a 10 kilogram mass here. If the 10 kilogram brick is not supported, so like if this was on a table, then it would just sit here, right? But if it's not supported by anything, nobody's holding it, it's not balanced with anything else, it's not on top of a surface, then think about what would happen. This is heavier, right? So it's going to create more clockwise torque, where this is going to have a little counterclockwise torque. So the little one's technically going to slow it down to an extent, but it's not going to make it stop. So we're going to have clockwise torque that wins. Okay, then a couple of things that we want to talk about here. Once we really get into pulleys and systems of pulleys, multiple pulleys working together, then we can get to some more interesting things. So one of the big concepts here is mechanical advantage. A mechanical advantage can actually be found a number of ways depending on what you're looking at. But from here, the way we need it is that your resistance force, or sometimes called your output force, divided by your effort force, which is sometimes called input force. Your output force or your resistance force is basically always going to be the weight of the thing you're trying to pick up. So here we have 100 newtons that we want to pick up. And what we're trying to figure out is how much effort is required to lift the load. Basically, how much force do you have to put in order to make this work? And so a couple of definitions and things we want to talk about. In general, mechanical advantage is basically how much more can you lift, right? So if I have an advantage of say 10 and I can pull with 100 pounds of force, then I can pick up 10 times 100 or 1,000 pounds of force with whatever setup. On the other side, you can look at it as how much easier it is to do something. So say I want to pick up 600 pounds and I've got some kind of setup, a lever maybe, that gives me an advantage of 5. That means it's going to be 5 times easier, or we divide by 5 to figure out how much force I put in. And because it can go, two different ways, and sometimes it's good to just plug in the formula and see what's going to happen. Okay? Now, mechanical advantage is technically going to be based off of the number of supporting strands and not the number of pulleys, but in most cases, they're going to end up being the same. So, like in a lot of our questions, we're going to have a certain number of fixed pulleys, a certain number of movable pulleys, and those together almost always end up adding to the number of supporting strands. What happens is you're pulling somewhere, creating tension, making force, and then that multiplies through the different strands that run through the sets of pulleys. Okay, so let's see what we can do with this. If we don't have to find the total number of pulleys or total number of strands, we don't have to draw anything out. We're just told. So the number of pulleys here, or sorry, the number of strands here is 4, means mechanical advantage is 4. Guess I'll write that here. And with the way that these pulleys transmit rotational motion, that tension rolls around one pulley, rotates, comes around another pulley, rotates, comes around another pulley, and then they get multiplied up and they work together. So that's what the significance is of the number of pulleys and the supporting strands. Okay, now if we want to solve for the effort, and last thing we can potentially do is a little bit of brute force algebra here. I can make this look like a proportion, and we've talked about this before, but proportions have these weird rules that you can actually swap your diagonal terms, and it would still give you the same answer. If you think about it, even if I put these in and swap their places, if I were to cross multiply like we normally do to solve, we'd still be multiplying the same two things together. So the nice thing about using this trick, though, is if I swap this up to the other side, then I get a formula that I can just work out and finish from here. So I don't know the effort that I need to put in, but I know that I'm trying to pick up 100 newtons, so that's what I need to get out of my system. And then the advantage that I'm going to get from using these different pulleys is 4. Again, you can think of it as it's 4 times easier to pick this up because of the way the tension gets multiplied. So to finish this up, I have 100 divided by 4, and so my effort force is 25. Okay, then similar idea, basically the same setup, but this time instead of looking at forces, we want to look at distances. So it's kind of interesting. We have a mechanical advantage formula. Before, we had FR over FE. And that's not going to work here because we don't have any force. I mean, technically, we're told this. We could calculate the one if we wanted to, but it's not asking about. So The alternative version of this formula is to use distances or velocities. The distance ratio or velocity ratio is basically just how those things stack and become equal to the mechanical advantage. What's strange about this, and it looks like it would be an error, but this time the effort is on top and the resistance is on the bottom. So this is intentional. So like this one had R on top and E on the bottom. This one has E on top and R on the bottom. So we definitely want it this way. What's going to happen is you're pulling a certain amount of rope out of the pulley system, and then that slack is going to split between all the different strands running up and down. So say I pull, 20 feet of rope out of this thing, then as I'm pulling 20 feet of slack, that's being spread across 4 different strands of rope. And so that's going to split and mean that the actual load, the thing that I'm lifting, is not moving as far. Okay, with this one, the load is always going to be your resistance or your output. So we are trying to solve for dr. And again, we can use that proportion trick to more easily get this formula. So we're going to have that dr is equal to dE over ma. Okay, so that's simple enough. I immediately write the wrong symbol. All right, there we go. So dr, thing we're looking for, the effort distance, so the person doing work, they pulled 4 meters of rope, so that's going to be 4m here, is divided by the number of strands that's going to be split across. So divided by 4, which I think is fairly easy to see. It's going to come out to be 1. Okay, then we want to look at basically the same formula. We've got a 200 Newton load. We are told 2 supporting strands, so technically we could cut that and find the effort that needs to go in. But this is asking about distances. How far? Okay, so then that means I want the formula with the dE over dr. Now it's asking how far the effort has to be moved. So if I want to pick something up 5 meters, and I have to remember that I need 5 meters to come out of each strand or rope that's supporting the weight, then I have to pull a lot further on the other end. This one we can use more of a normal proportion setup. I want to solve for dE so I can cross multiply. The nice thing is 1 times dE is basically just going to separate that. Then in the other direction, I have the mechanical advantage times the resistance distance, which is basically how far the load's actually going to move. I don't know what dE is. That's the question. The mechanical advantage is going to be 2 because we're directly told how many supports we have. And then that's going to multiply by the distance that the load is moved, which is 5 meters. So that's going to give us a total of 10 meters, right? Because remember, there's 2 supporting strands. You're net with 5 and 1 rope, 5 on the next rope, and there's your 10. Okay, then 2 more. We're almost done with this group. We want to find the actual mechanical advantage of a system that can lift a certain number of grams using another number of grams. Now, technically speaking, this should be done with forces. But if everything's under the influence of the same gravity, then we can assume gravity is constant in all these places and technically cancels out. So let me show you how that works. Mechanical advantage is what we've been saying. These formulas, though, don't discriminate, so I can swap that to be AMA, and it'll work the same. So where I used to have FR over FE, if I'm looking at these as objects hanging on a pulley system, then I'm going to have a mass times gravity and another mass times the same gravity. And so gravity cancels, and really I can just look at the ratio of the masses. Okay, and so if I do that, it means I don't have to convert these things, I just need to match. So nice little shortcut with this, it saves us a little trouble. The thing I'm trying to lift is going to be the resistance that I'm working against, or again, you can think about as input-output. That's the force I need to put out, or the equivalent mass that I need to put out to pick up. So this is my MR. And then what I'm using or what I'm doing is my effort, my work that I put in, that's going to be ME. So really all I need to do is divide them. And because they both measure in grams, grams will cancel grams, and that's just gone. there are no units on this, so it's not that they were left out of the question or left off of the choices. There's just intentionally nothing here. It's a ratio, basically, of how much help you get from a system. So dividing these, you get something like 3.0307, which looks closest to the bottom one. Okay, and then the last one for the group, thinking about a similar concept, but we want to find this as an efficiency, right? So we have this formula. Efficiency is AMA, so actual mechanical advantage, divided by IMA, which is ideal mechanical advantage. Basically, how well does it work versus how well is it supposed to work? And then multiply by 100% to scale it to a percent. Okay, well, one part's nice. It does directly tell us that the IMA is 3, but it doesn't tell us the AMA. However, we can use the information we learned on the last question, we can put together and find one. So AMA, using that slightly modified formula from earlier, is going to be MR over ME. Remember, there technically should be gravity, but it can be canceled in a hanging pulley system. Okay, well, the MR, the mass we're trying to balance or pick up, is 600 grams, and the ME is what we're putting in or balancing on the other side. Grams and grams will cancel, which again is why we weren't super worried about the conversion. And this is going to give us excuse me, about 2.83. Okay, and then now that we've learned that piece of information, let's see what we can do that we couldn't do before. I know my AMA, I know my IMA, and I've got formulas where they want to go. So let's finish it up. The AMA was 2.83, the IMA was just 3. Typically for pulleys, IMA is counted based off of number of ropes or pulleys. So typically your IMA is just a whole number like this. And so we can see we're a little bit off, but it's hard to tell right now if it's good or bad or what that means. And so if we run these out, divide these, 0.943396, so on, and then multiply by 100. Looks like it's very slightly different on the rounding, but I'm getting something like 94.34. So yeah, it rounded a little bit funny somewhere, but that's obviously still the closest one. Okay, and for this group of material, that's it.